In this research paper titled, Functional Abstraction of Knowledge Recall in Large Language Models, authors Zijian Wang and Chong Xu from the University of Sydney explore how large language models, or LLMs, remember and retrieve information. These models, based on pre-trained transformers, are incredibly good at recalling facts, but we don't fully understand how they do it internally. The paper aims to make this process more transparent by treating it like a computer function. To start, LLMs act as vast knowledge bases, storing information about the world and pulling it up when needed. For example, if you ask about a subject and a relation, like, what is the capital of France? The model might output, Paris. But inside the model, this recall happens through hidden activation spaces, essentially, the internal computations in the neural network. The authors propose that these activations can be thought of as executing a function, with clear components. Input arguments, a function body that does the work, and return values. Specifically, they suggest that for knowledge recall, the model's activations create a mapping function based on the relation. The subject, like France, serves as the input argument. The relation, such as capital of, defines the function's operation. And the object, like Paris, is the return value. This idea comes from observing how tokens, those basic units of text in the model, have activation vectors that align with these functional parts. The paper builds on previous work in interpretability. There are two main approaches others have used. One is module-based, where researchers look at specific parts of the model's architecture, like neurons or weights, to see how they handle knowledge. This gives a low-level view but requires a lot of manual effort and might not scale well. The other is representation-based, which focuses on what information is encoded in the model's activation space. The authors follow this second path, treating the activations as representations that can be mapped to an algorithm. To test their hypothesis, they designed a three-step method. First, they formulated the idea that knowledge recall is like running a function in the activation space. They drew from concepts in knowledge graphs, where relations act as transformations between entities. In the second step, they located the key representations in the model. They used a technique called activation patching, which involves swapping or modifying parts of the model's activations during processing to see how it affects the output. This helped them identify which activation vectors are knowledge-aware and align with the function's components, like inputs, the main processing, and outputs. For the third step, they conducted experiments to verify this. They created a patching-based knowledge scoring algorithm. This algorithm scores how much certain activations contribute to recalling knowledge. By patching, meaning altering specific vectors, they could isolate and test each functional component independently. For instance, they might patch the subject-related activations and see if it changes the output, confirming that those vectors act like input arguments. They also did counter-knowledge testing. This involved feeding the model conflicting or incorrect information and observing how patching different components affected the recall. The results showed that each part of the activation space behaves somewhat independently, like separate variables in a function, which supports their abstraction. Building on this, the authors improved a technique called contextual knowledge editing. Normally, editing knowledge in LLMs can be tricky because the model might forget new information quickly. By using activation patching, they rewrote incoherent or conflicting activations in the context. This allowed the model to better retain short-term memory for new facts. For example, if you want the model to remember a custom fact, like changing Paris to something else as the capital, patching the relevant activations helps make that change stick without disrupting the rest of the knowledge. Throughout the paper, they reference related studies. For instance, works by Petroni and others showed LLMs as knowledge bases, while Zhang and colleagues demonstrated how models predict objects from subjects and relations. They also cite representation-based methods from Zhou and von Rutta, which analyze what the model learns in its activation space. One key illustration in the paper is a figure showing how knowledge-related representations are locally distributed and aligned with functional components. In a simple recall process, like subject relation to object, the activations cluster around the input, the mapping, and the output, making it easier to visualize and manipulate. Overall, this functional perspective offers a higher-level way to understand and control LLMs. By abstracting knowledge recall into a function-like structure, we can make these models more interpretable and reliable for real-world applications, such as acting as assistants without unexpected errors. This approach could pave the way for better tools in AI safety and knowledge management, ensuring that LLMs handle information more predictably.